All right, welcome to another deep dive. Today, we're going deep into algebraic propositional logic. You know that Stanford Encyclopedia philosophy entry you gave us?
Oh yeah, that one. Quite a read.
It is quite dense. So basically, we're going to try to extract the key knowledge from it. We want to make it, clear and understandable, especially for someone coming at it maybe from more of a philosophy background.
Right, because, you think logic, you think philosophy, right.
Mm-hmm.
But then suddenly we're bringing in algebra.
Yeah, it's this fascinating intersection of these two seemingly quite different fields. But as we're going to see, they're more connected than you might think.
Much more.
So maybe a good place to start is with George Boole. He was one of the first to really present logic in this algebraic way back in the 19th century. What was so groundbreaking about his approach?
Well, for Boole, and really a lot of thinkers at that time, they didn't really make a super strict separation between the formal language of logic and what we now call mathematical semantics.
Okay, so they weren't as concerned with separating the symbols from their meaning.
Not as the same way we are today. They were building these algebraic theories, like Boolean algebras, and they were already thinking about them in terms of their logical interpretation. So, the algebra was very much intertwined with the logic.
It wasn't like logicians came up with a system and then mathematicians said, oh, we can represent that with algebra.
No, it was more integrated, more like a unified way of thinking about things.
Interesting. And then things kind of shifted, right? With Frege and Russell.
Yes, with Frege and Russell, there was a definite move towards focusing on formal languages, on these things called deductive calculi, which, by the way, are also sometimes called Hilbert-style or Frege systems, just so you know.
Right. Deductive calculi, so systems with axioms and really specific rules of inference.
Precisely. And this was a big difference from Boole's approach. I mean, one of the key things is that Frege and Russell, at least initially, they didn't really have a fully developed formal semantics for their systems. They were more interested in the syntactic side, the structure of the language, and the rules of derivation.
So they were building the machinery of logic, but not necessarily giving a precise mathematical account of what it all meant.
That's a good way to put it. They relied more on intuitive interpretations. They knew what they were aiming at, what kind of logical reasoning they wanted to capture, but they didn't necessarily translate that into a rigorous mathematical framework for meaning, at least not at first.
So we have this period where the emphasis is really on these formal proof systems, these rules of deduction.
And this approach was very influential. It led to the development of all sorts of non-classical logics, like modal logics, intuitionistic logic.
Right, systems that went beyond the traditional classical logic.
Exactly. And again, these new logics were often presented in this axiomatic, proof-theoretic way without initially a fully formal semantics.
It's interesting how the focus seemed to be more on the how of deduction, the manipulation of symbols according to rules, rather than a precise mathematical account of what those symbols were supposed to represent.
It's a subtle but important point.
Mm-hmm.
But then you have Tarski coming along, and he really kind of shifts the focus back to this notion of logical consequence.
Right. The idea that one statement follows logically from others. Why was that shift so important?
Well, Tarski, in his work, which spanned decades, he gave us these really rigorous definitions of logical consequence, both semantically in terms of truth preservation and syntactically in terms of derivability. And this was pivotal for the development of algebraic logic because it gave us a really clear target, how to capture this notion of consequence in an algebraic way.
So by focusing on logical consequence, Tarski provided the link between the world of algebraic structures and the world of logical reasoning.
Precisely. He gave us a way to think about consequence in a very abstract, general way, which, as it turns out, aligns beautifully with the way algebra works.
Okay, I'm starting to see the connection. And then you mentioned the emergence of things like algebras and logical matrices in the 1920s. These start to be used as models to provide a formal semantics. Can you break those down a bit? What are they, and how did they start to give us a more concrete grasp of meaning and logic?
Sure. So a logical matrix, think of it as like an algebra with a little something extra.
Yeah.
You have an algebra, right, with its operations that correspond to our logical connectives, A, N, D, or not T, and so on. But then you also have a special subset of elements in that algebra. This subset, you can think of it as representing, in a way, truth or designatedness.
So it's like picking out the elements in the algebra that correspond to the true propositions.
Exactly. And these matrices, they allowed logicians to give these formal interpretations to logical systems, like A formula is considered true in a matrix under a certain valuation if it ends up in this special designated set. It's like we're playing a game on this algebraic structure, and landing in the designated set means you win.
I like that analogy. So these matrices gave us a way to ground the abstract symbols of logic in these concrete mathematical structures.
And this naturally led to the idea, well, if we can model logics using these algebraic structures, can we then use what we know about algebra to understand logic better?
Which brings us to the definition of algebraic logic itself. It's the study of logics, right, by associating them with these classes of algebras, matrices, and related structures.
That's the gist of it. It's about looking at logic through the lens of algebra. And the hope is that by doing so, we can uncover some deeper structural similarities between logic and algebra, maybe prove some general theorems about families of logics, and get a better understanding of what logical consequence, truth, and validity really mean.
It's like finding a new language, the language of algebra, to talk about the old philosophical problems of logic. And this leads us to the development of a more general theory of algebraization. The sources mention this kind of gradual emergence of a general theory, culminating in the concept of an algebraizable logic in the early 1980s. What was the motivation behind that? Why was a more general theory needed?
Well, at first you have these sort of isolated cases of algebraizing specific logics, like Boolean algebras for classical logic. But then people started to wonder, can we do this systematically? Can we find a general framework for relating the properties of any logic to the properties of some corresponding algebraic structure? And that's what led to the idea of algebraizable logic, which is a kind of logic that has a particularly well-behaved algebraic semantics.
Okay, so algebraizable logics are the ones that play nicely with algebra. And that brings us to abstract algebraic logic, AAL. We're focusing on the algebraization of propositional logics viewed as consequence relations. But to understand that, we first need to grasp this idea of an abstract consequence relation. How does that work? How do we abstract away from specific logical systems?
Well, you have to go back to Tarski again. He was really interested in this idea of a consequence operation. You take a set of premises, and this operation gives you all the statements that follow logically from them. And he identified these key properties of consequence operations, like anything that you start with is already a consequence of itself. Or if you apply the operation twice, you don't get any new consequences. And an abstract consequence operation, it keeps some of these core properties, like if A follows from X, then A also follows from any bigger set that includes X.
Right, so it keeps this idea that if you add more premises, you can't lose any of the conclusions you already had.
Exactly. And then there's this related notion of an abstract consequence relation, which is just another way to formalize the same idea. It's a relation between sets of formulas and formulas.
Yeah.
And it also has to satisfy certain properties, like reflexivity. If a formula is in a set, it's a consequence of that set. And transitivity. If A follows from X and B follows from Y together with A, then B follows from X and Y together.
Okay, so these abstract notions of consequence, they give us a kind of framework for what it means to have a logical system at all before we even get into the specifics of any particular logic.
Precisely. And it's worth noting that these ideas of closure operations, which consequence operations are an example of, they pop up all over mathematics. Like in topology, you have the closure of a set. In universal algebra, you have closures under operations. So it's a very general and powerful concept.
So given these abstract foundations, how do we define a logic in this framework, especially when we're thinking about it from a more philosophical perspective, focusing on the structure of reasoning?
Right, so in AAL, a logic system is defined as a formal language, together with a consequence relation on the formulas of that language. But the key is that this consequence relation has to be what we call formal or structural.
What does that mean, formal or structural?
It means that if a set of formulas, let's call it gamma, entails a formula, let's say phi, then if you uniformly substitute the propositional variables in those formulas with any other formulas, that entailment still holds.
So it's about this idea that logic should be about the form of arguments, not about the specific content. Like, if all men are mortal and Socrates is a man, therefore Socrates is mortal is a valid argument, then any argument with the same structure should also be valid, regardless of what you substitute for men, mortal, and Socrates.
Exactly. That's the essence of it. And this formal language, it's built from propositional variables and logical connectives, just like you'd expect. And you could build more and more complex formulas using those. And then a substitution, it's just a mapping that replaces those variables with other formulas.
Okay, that makes sense. And then a logic system is just this pair, the language and this special consequence relation.
Right. And if the consequence relation is finitary, then the logic is finitary, which means that if something follows from an infinite set of premises, it must also follow from some finite subset of those premises. These consequence relations, they can be defined in a couple of ways. You can have a proof-theoretic definition based on axioms and rules of inference, or you can have a semantic definition based on some notion of models and truth.
Right, and then there's this idea of soundness and completeness. A sound-proof system only derives semantically valid consequences, and a complete one can derive all of them.
That's the ideal.
Yeah.
A proof system that's both sound and complete, capturing exactly the intended notion of logical consequence. And then, within a logic, we have these things called theories, which are just sets of formulas that are closed under the consequence relation. And a theorem is a formula that follows from the empty set of premises a logical truth.
Got it. And then the sources mention a bunch of examples of logics: classical propositional logic, intuitionistic logic, different modal logics. It's nice to see that this framework can handle all these different systems.
Absolutely. Classical logic, it's one we usually think about, with truth tables and all that. Intuitionistic logic has a different approach, focused on the idea of constructive proof. Modal logics introduce new concepts like necessity and possibility, and this framework is general enough to accommodate all of them.
So we've got this abstract view of logic, right, in terms of consequence relations. Now, how do we connect that to algebra? The sources talk about seeing propositional formulas as terms in an algebraic language. What's the idea there?
It's actually pretty straightforward. We take those logical connectives like A and D, or R, not T, and we treat them as operation symbols in an algebra. So if you have a binary connective like A and D, it becomes a binary operation in the algebra. And propositional variables, they just become variables in the algebra like X and Y.
Okay, so it's like we're reinterpreting the syntax of logic, the way we build formulas within the language of algebra.
Exactly. And this allows us to do some really cool things. For example, we can now interpret these formulas, which we're now thinking of as terms, within specific algebraic structures. So you have an algebra, and it has a set of elements. And then each operation symbol in the algebra corresponds to a function on those elements.
So it's like the algebra provides a concrete domain of interpretation for the formulas.
Right. It's like a model in standard semantics, but with algebraic structure. And evaluation, it just assigns elements from the algebra to the propositional variables. And then you can extend this to interpret any formula, giving it a value in the algebra.
So it's like we're giving the formulas meaning within this algebraic world.
Exactly. And then on top of that, we can take the set of all possible formulas and treat that as an algebra itself. It's called the algebra of formulas. And this becomes a key object in studying the logic algebraically.
Okay, so we have this way of interpreting formulas in algebras, but to really exploit that, we need to bring in some heavier machinery from universal algebra, things like congruences, homomorphisms, varieties.
Right, these concepts give us powerful tools to analyze these algebraic interpretations. A congruence, you can think of it as a way to identify elements in the algebra that are, in a way, indistinguishable from the point of view of the logic. And a homomorphism is a mapping between algebras that preserves the structure. And varieties and quasi-varieties, they're special classes of algebras defined by equations and quasi-equations.
Right, so we're using these algebraic notions to study the structure of the interpretations themselves.
Precisely. And the key is that if a logic corresponds to a certain variety of algebras, then the properties of that logic must be reflected in the algebraic properties of that variety, and vice versa. So we can translate questions about logic into questions about algebra, and vice versa.
Got it. And then this brings us to the more formal notion of algebraic semantics, which you alluded to earlier. The prototypical examples are Boolean algebras for classical logic and Hating algebras for intuitionistic logic. How does this work? How does the algebraic semantics actually define the logical consequence relation?
Well, in these cases, you get this really nice completeness result. Like for classical logic, you can say that a set of formulas, gamma, entails a formula, phi. If and only if, in every Boolean algebra and every evaluation, if all the formulas in gamma evaluate to the top element of the algebra, which represents true, then phi also evaluates the top element.
So it's like saying that logical consequence is equivalent to this algebraic property of preserving the top element.
Exactly. And a similar thing holds for intuitionistic logic and hating algebras. But the idea of algebraic semantics can be even more general. You could have designated sets that are defined by equations or even relations. And the key idea is that logical consequence corresponds to preserving this notion of designatedness within the algebraic models.
Okay, that's a pretty powerful and flexible framework. But then we also learned that not all logics have this kind of neat algebraic semantics. And that's where logical matrices come in. They're supposed to be even more general.
Right. So a logical matrix It's basically just an algebra, together with a designated subset of its elements, without any requirement that this subset be defined by equations or anything like that. It's a very simple but very general concept. And the crucial thing is that every logic, no matter how complex or weird it might seem, it always has a matrix semantics.
Okay, so matrices provide a universal semantic framework. And then within matrices, we have this notion of the Leibniz congruence.
The Leibniz congruence. This is a really important concept. It's the largest congruence relation on the algebra that respects the designated set. Basically, two elements in the algebra are related by the Leibniz congruence if they are logically indistinguishable with respect to the logic.
So it's like finding the finest grain of distinction that the logic can make within the algebra.
Exactly. It tells you which elements of the algebra you can identify without losing any information about the logical consequence relation. And then there's this really cool technique for proving completeness called the Lindenbaum-Tarski method.
Tell me about that. Why is it so important?
Well, the Lindenbaum-Tarski method, it gives you a way to construct algebraic models directly from the logic itself, using the theories of the logic. Basically, you define a congruence relation on the algebra of formulas, and then you form the quotient algebra. And this quotient algebra, it turns out, is a model of the logic.
Wow, so you're building a model out of the syntax of the logic itself.
That's the beauty of it. It shows this really deep connection between the syntactic structure of the logic and the semantic properties of its algebraic counterparts. And then you have this notion of the natural class of algebras associated with the logic. But it turns out there might be different ways to define this.
Right. The sources mention a couple of different approaches. What are the philosophical considerations here? Like, what makes one class of algebras more natural than another?
It's a good question. One approach focuses on these things called reduced matrix models. These are models where the Leibniz congruence is the identity relation, meaning you can't identify any elements without losing logical information. And then there's another approach that uses the Susko congruence, which is a more sophisticated way of identifying indistinguishable elements. And the philosophical issue is like, which one of these best captures the essential features of the logic? Which one is the most faithful algebraic reflection of the logic?
It's like we're trying to find the best algebraic mirror for the logic, the one that shows us the most accurate reflection. And then we come to the concept of algebraizable logic, which seems to be like the gold standard, the strongest connection between logic and algebra.
Absolutely. When a logic is algebraizable, it means there's this incredibly tight relationship between the logic and a specific class of algebras. There's a one-to-one correspondence between logical consequence in the logic and equational consequence in the algebra. So you can translate back and forth between logic and algebra without losing any information.
That's amazing. And this has all sorts of implications, right? Like, you can use algebraic techniques to prove things about the logic or logical insights to understand the algebra.
Exactly. It's a very powerful connection. But then there are these logics, like that local modal logic K, that aren't algebraizable.
Right, so not everything fits perfectly into this algebraic framework. What does that tell us? Why aren't all logics algebraizable?
Well, it's just that there are limits to how far you can push this algebraic approach. Some logics might just have features that are inherently more proof theoretic or model theoretic, features that don't translate so neatly into algebra.
It's like there's a certain kind of logical reasoning that algebra is really good at capturing, but maybe there are other kinds that are more elusive.
And this brings us to the Leibniz hierarchy, which classifies logics based on how well behaved their Leibniz operator is. This hierarchy gives us a way to measure, in a way, how algebraic different logics are. Some logics, like the equivalential and algebraizable ones, they're at the top of the hierarchy. They have this really nice connection to algebra. And then there are others that are further down, meaning their connection to algebra is weaker or more subtle.
It's like a spectrum of algebraic potential for different logics. And then there's these other hierarchies too, like the Frege hierarchy and self-extensional logics, suggesting that there are different ways to classify and understand the world of logic.
It just shows you how rich and complex the world of logic is. And algebra provides this really powerful lens to analyze and study it.
So to wrap up, we've gone on this deep dive into algebraic propositional logic. We've seen how algebra and logic are interconnected, offering a fascinating new perspective on the foundations of reasoning.
It's a beautiful and powerful framework, one that has a lot to offer both philosophers and mathematicians.
So for you, our listener, we hope this has given you a taste of this rich and rewarding field. You now have a sense of how algebraic structures can be used to model and understand logic, and maybe you've started to wonder about the limits of this approach, about what aspects of logic might resist this kind of algebraic analysis. These are deep and fascinating questions, and we encourage you to explore them further. Thanks for joining us on this deep dive.